Water wheels harness the power of water by using gravity, which causes water's weight to turn a wheel that can then be connected to a machine.
In America's history, water wheels were important because they allowed American manufacturers to produce goods here on American soil instead of having to depend on England for their daily needs.
Small mills and large factories produced a variety of goods, including cloth, millet, yarn, and planks.
We visited Old Sturbridge Village, a working replica of an old mill village in Sturbridge, Massachusetts, and the Songus Center, a national park depicting different aspects of life in a factory town in the 1800s in Lowell, Massachusetts, to learn about a variety of different water wheels. As we said, gravity pushes or pulls the weight of water down onto the paddles or buckets of a water wheel, causing it to spin and generate power. Humans have used water wheels for a very long time, but have adapted them to suit their geographical environment.
Each new water wheel was developed to make the most efficient use of a river with the different values of head and flow.
So what do we mean by a river's head and flow? Well, it all depends on the geography of the river.
The scientific term head describes how much the water drops towards sea level within 1 yard. This depends on how steep the slope of the land is. A river that's water falls a longer distance towards sea level has a high head. A river that's water doesn't fall as sharply towards sea level has a low head.
The term flow describes the amount of water passing down the river every second. A river where a large amount of water passes every second is called high flow. A river where a smaller amount of water passes every second is called low flow.
When setting up a water wheel, a channel, called a raceway or canal, is dug parallel to the river. Because the head and the flow depend on the geography of the land, the head and flow of the channel mimic that of the river. An undershot wheel works most efficiently with a river that has low head and high flow.
An overshot wheel is powered by water falling into buckets on top of the wheel, so it is used in rivers with a high head and low flow. Water enters the breast to about halfway between the top and the bottom of the wheel on the upstream side. The breast wheel is efficient in a river with medium head and medium flow.
A tub wheel like this one in the carding mill at Old Sturbridge Village also works well in a river with medium head and medium flow. The reaction wheel and turbine are similar to each other and are still used today, particularly in dams with hydroelectric facilities.
Water wheels were a very important part of America's industrial history. This technology changed the way that people that lived in the 19th century worked.
Now that we have a source of power, how do we get the force of the water wheels to run the machines? Gears and pulleys were used beginning in the 18th century when rivers were harnessed for the power their water could provide. They were used to transfer the power of the water, turning the wheel to run machines in grist mills, carding mills, sawmills, and several other types of mills.
All gears work using teeth, rods, or pegs. These allow them to intermesh with each other, so when one gear turns, the other one turns in the opposite direction. Pulleys and belts are used to transfer power from one gear to another. Belts are flexible bands made of leather, cloth, rubber, or plastic that connect two separate pulleys so that when one turns, the other one will turn. At Old Sturbridge Village, we learned how gears and pulleys help operate the mills there.
Here we see the carding mill at Old Sturbridge Village. This carding mill uses a tub wheel. The wheel is connected to 3 crown gears. A crown or bevel gear is a gear that meshes at a right angle. It can change the direction of rotation by 90 degrees and therefore transfer the power around a corner. In the carding mill, these gears connect to shafts that connect to pulleys that come through the floor and bring the force of the water to the machines upstairs on the mill floor. The machines comb and twist the sheep's wool to create loose strips of wool called skeins. Once the carding mill came into being, this task could be done in 10 to 30 minutes. Using machines for this work saved women hundreds of hours of work per year.
Gears were used in the 19th century for many things, including mass production mills like this Lowell textile mill. The gears and pulley system worked the same here as it did in the small town mills. The difference was in the size of the operation. In the little textile mills, complicated systems of gears and pulleys transferred power from the turbine water wheels to operate the machinery. As in the small town mills, factory owners chose the best type and size of gear system for each job. A rack and pinion gear system uses one gear, the pinion, which meshes with a flat gear called the rack. This combination converts a circular or spinning motion to a linear or back and forth motion. This type of gear system was used to run the looms. Pulleys are used in these mills as often as gears and maybe more often. Pulleys are less expensive, lighter, easier to replace, and they can carry the water's power a longer distance than any one gear could, but gears are capable of more power.
Even now, gears and pulleys continue to be used in electronics, cars, watches, and other types of machines. Almost every type of machine uses a gear or pulley system.
Generators, turbines, a flowing river, and a dam are the most important materials that you need to create electricity using water power. Small businesses which use a generator to create hydroelectricity to help their business, and large plants built exclusively for harnessing and distributing water power both exist right here in New England.
We visited Amoskeag Fishways, a hydroelectric plant on the Merrimack River in New Hampshire, to learn more.
Okay, right here, and looking in back of me, you can see the Amoskeag Dam. It's 700 feet long, and what you see on the other side of the dam is what we call the Amoskeag Gatehouse. Okay. Now the dam is hollow. A lot of people don't know that, but when they built the dam, they created a tunnel through the center of the dam. This way here they could get from the powerhouse over to the gatehouse.
The process of creating hydropower begins when the river water fills up the reservoir behind the dam. This reservoir can also be called a mill pond. Gravity directs the water from a reservoir through narrow openings called penstocks, which go into a powerhouse. The water is captured by turbines, which are like modern water wheels. Water pressure makes the blades on the turbine spin, converting the kinetic energy of boiling water into the mechanical energy of a spinning wheel. Then, a generator converts the mechanical energy of the spinning wheel into electrical energy.
The electrical conversion, called electromagnetism, is too detailed for us to explain in this short video, but you can go to www.vic.com/hydroworks.htm and you can click on generators to learn more. Now back to Amoskeag Fishways.
When the electricity leaves the generator, it travels along a copper wire to the transformers. Transformers control the voltage of the electricity, which is then sent to homes and businesses across New England.
We also visited Riverdale Mill in Uxbridge, Massachusetts, a small business powered by their own hydroelectric generators.
The Riverdale Mill was built next to the Blackstone River, where the geography was right for creating a mill pond behind a dam on the river.
Everything in the mill, from lights and computers to the factory's machines, runs on electricity produced by water power. Electricity is also an important part of how they actually create the wire mesh that the company produces. Wire has electricity shot through it, and that short circuits the current, and the heat produced from that melts the wire together.
We had the chance to meet the owner of Riverdale Mill, Mr. James Knott, and ask him a few questions about hydropower.
How does hydropower help your business?
It helps us by lowering our costs so that we can pass our products along to our customers for less money. It's because we keep our costs down, and hydropower is one of the things that keeps the costs down.
What are the pros and cons of hydroelectric power?
There are endless pros to hydropower. We're not burning fossil fuels. There's only a limited number of fossil fuels on this planet, And when we turn them into gas and send them up into the air, of course, that is what has contributed to global warming. That's why the Arctic is getting smaller. And the most important or equally important thing is that we don't put any carbonaceous particles into the environment, particles that we and all other living things inhale and can damage us and other living things.
Using hydroelectricity is a positive step for both Mr. Knott and the environment, but there are some drawbacks. Building a dam for hydroelectric power production may require the flooding of entire valleys and other areas, which disrupts natural seasonal changes in the river and which can cause ecosystems to be destroyed. Another problem with building a dam is that it can destroy a fish's habitat and prevent fish from spawning because they cannot jump over the dam to swim up the stream.
But people have developed an innovative solution to this problem by building fish ladders, like this one at Amoskeag.
And the way it works is in the springtime, in May and June, at the time of year these fish would come up the river, this very large metal gate behind me is actually lifted up. That allows water from the reservoir behind me to flow into the fish ladder and through the fish ladder and down the hill. And it allows the fish to have basically a passageway where they can swim through the ladder, up the waterfalls in the ladder to be able to get around the dam. So then they can come out of the fish ladder right here where the water comes in, get out into the reservoir, and continue on their way up the Merrimack River to where they need to go to spawn.
Right now, 10% of the United States electricity is using hydropower, and 20% of the world's electricity is using the power of water.
Hydroelectric plants generate power from water flowing through watersheds, and this power is a clean and, most importantly, a renewable source of energy.